Hello everyone and welcome to the second lecture. So in this lecture we will be deriving the governing equations of the phase field model, and we will also discuss one solution method in order to solve for the phase field and the displacement field. And at last, I will be discussing an implementation in the software Abacus. And finally, I'll be ending by showing some simple linear elastic brittle fracture problems and how did we use phase field in order to solve the crack path. So just to recap, we had a domain omega where we had a crack. This crack was regularized by a phase field contour, which was again regulated by this parameter LC, which was called the length scale parameter, correct? Phase field is a field variable that is represented by phi of x, and capital gamma is the surface area, or it's the crack surface area. This body is subjected to external tractions and displacement conditions, and there is a body force. Okay, so phase field model PFM is a diffuse crack model where the discontinuity or crack is not sharp but smeared with a crack width LC, and its contours are expressed in the form of a phase field variable phi, which goes from 0 to 1, where phi equals to 0 means there is no crack, and when phi equals to 1 there is a crack. The crack propagates along a path of minimum total energy, which is the internal bulk energy plus fracture energy minus external work done. Okay. Next, it is a variational approach to fracture. Why? Because it involves a variational function. And lastly, this is the most important assumption, as we discussed in the previous video. Crack growth is irreversible. So we have to assure that phi dot is always greater than or equals to 0. The crack cannot heal itself. So this is essentially a coupled problem in displacement and phase field. So what are our solution methods? So for solution methods, we will start with this operator split algorithm, also known as the staggered formulation. So if you remember from the previous video, I will link it up at the top. This was the total energy functional that we derived, correct? Capital E. This term is a function of displacement and phase field. Of course, G of phi is your degradation function, and psi 0 is the strain energy of the uncracked specimen. Next, B dot U and T bar dot U are the external work done, which is only a function of displacement. And third term is essentially the fracture term, which is GC multiplied this crack surface energy density function, which is a function of only phase field. So with reference to this previous diagram that I showed you, we can split this problem into three parts. First, if you see this part, here there is no crack. So there is essentially the traction boundary and the displacement boundary without the crack. That is the body force. Everything but the crack. In the second one, you have only the crack. So it is only phase field. Here it is only displacement. Here it is only phase field. And in the third one, you don't have anything. You just have the body with no boundary conditions, no cracks or something, and we denote it by this capital H, or as we will see it later, by capital phi. Capital phi. The phase field, this phi is a small phi. We will denote this capital H. It is also called the history field, as I will tell later. This history field area or region by also capital phi. So we denote pi u as the displacement functional, and we take this term. This term is essentially what? It is the strain energy of the cracked specimen, correct? So psi will be equals to G of phi into psi 0 according to isotropic formulation. And if you are doing an isotropic formulation, you know what to do from the previous video. So we take this term and we take this term and this term and we club it like this. The first two are a volume integral and the third one is a surface integral. So we get a displacement functional. The second one is pi phi. It is a fracture functional. So we take this term, which is only a function of phase field, keep it here, and we take also this term, which is g of phi into psi of 0, and we keep it here, but we replace this psi of 0 by capital phi. And as I said, this capital phi comes from this layer. This layer is called the history layer. So what is this capital phi? Capital phi is called the energy history, where it is essentially psi 0 at a previous time step if psi 0 is greater than capital psi at that time step. Otherwise, you just take the previous capital phi n. So let me explain this in more simple words. You have different time steps, Tn, Tn plus 1, Tn plus 2, etc. So at Tn plus 1, you calculate the strain energy of the body due to crack propagation. Okay? If that value exceeds the strain energy of the previous time step, you preserve this value. And if it doesn't, you take the strain energy of the previous time step itself. So you discard it. Again, if in the current time step, the value of the strain energy is greater than that of the previous time step, we consider the value of the current time step. Otherwise, we discard it. We take the value of the previous time step. This is called energy history. Why history? Because it depends on the values of the previous time steps. That is why it's a history. So I think you understood what we did here. This term was a function of displacement and phase field. This was displacement and this was phase field. And so essentially when we break the problem into these three layers, we club all of the displacement functions separately, we club all of the phase field functions separately, and we use this history field in order to interact between these two layers. Okay? So we take only displacement functions and displacement functions in the displacement functional. We take the fracture function and fracture function in the form of our energy history in the fracture functional. Okay, so we are essentially decoupling the total energy density functional. I'm sorry, the total energy functional. Okay. So continuing, we have pi u and pi phi. So remember, we have to extremize this total energy functional in order to solve for the phase field and the displacement. So we take pi u and pi phi and we individually minimize them now. So essentially, if pi u and pi phi are being individually minimized, automatically your capital E will be minimized. So we minimize pi u and pi phi separately and we derive the strong form of the phase field model. Strong form is essentially the governing equations and the boundary conditions. So it looks like this. For the first one, where we minimize pi u, we get these set of equations. The first one is the equilibrium equation, which you may know from your elasticity courses. Grad sigma plus b equals 0 in omega in your domain. And these are the boundary conditions. So you have the traction boundary condition and you have the displacement boundary condition on the respective boundaries. For the second one, del pi phi equals 0, we get this set of equations. So this is essentially what? Only dependent on phase field. You see, 2 into 1 minus phi into capital phi is your energy history, minus gc by lc into phi minus lc squared into the Laplacian of phi equals to 0 in omega, and this is your boundary condition, which is essentially what? In capital gamma, so in your crack surface. Okay. So this term, which contains capital phi or your energy history, is called the crack driving force, or it is the crack driving force term. So if you take this term and take it here, like change the sides of the equation, this will be equals to this, correct? So essentially, this is the crack driving force and this is the crack resistance. Why? Because in critical conditions, if you remember from the Griffith's formulation, when G reaches GC, then only your crack starts propagating, correct? Then only your crack becomes critical and it starts propagating. So essentially, something is equals to GC multiplied by something, okay? So this GC being a material parameter, this will resist crack growth. And when this previous term is equal to the term containing GC, that means it has already reached criticality. So it is overcoming the crack growth resistance. Okay. So this second term is essentially your crack resistance term and this term is your crack driving term. Okay. So these are the governing equations for the displacement problem and these are the governing equations for the phase field problem. So we have essentially decoupled the the entire formulation using this history field. Now we discuss the finite element formulation of it. So we have pi u and pi phi and our ultimate goal is to reach the Griffiths problem because the Griffiths formulation is the mother of all fracture formulations and every problem or every variational formulation will eventually gamma converts to the Griffith problem, as I told you in the previous video, correct? So when this happens, we say that pi and u are the solutions of the extremization problem of pi u and pi phi respectively. So phi n plus 1 will be what? Argument under infimum of pi phi. INF is called infimum and ARG is the argument. So essentially, infimum of pi phi, this is the extremization problem and its argument is phi of the next time step. Okay, that's why you have infimum of phi, phi is written down of pi phi. So infimum of pi phi, argument of it is essentially phi, and likewise infimum of pi u, the argument of it is essentially un plus 1 or your displacement. Now when you convert it to the finite element equations, you will get something like this, correct? This you may be familiar from your finite element courses. So essentially this is a overall stiffness matrix where K phi phi, K phi u, K u phi and K u u are the individual stiffness terms containing phi and u, which is again coupled and decoupled. So essentially K phi u and K u phi are coupled, phi phi and u u are decoupled. Okay, so this is essentially a function of only phi. This is only u, this is, and this are u and phi. So this multiplied by your primary variable vector, which is phi and u, will be equals to minus of the residuals. Okay. So in finite element formulation, we are all aware of these terms where phi u, they are all split in terms of their shape functions, individual shape functions, n of phi and n of u, and grad phi and grad u by the individual derivatives of shape functions b of phi and b of u. So this capital B matrix are the derivatives of the shape functions. So again, if you have a 3D element, you have Z. If you don't have a 3D element, you don't have Z. That's it. So these are the individual expressions that you will get after, solving that entire capital E or the total energy functional. So you can try it out and, verify your results from this. So R phi and RU are these terms, the residuals. RU is F external minus F internal. R phi is this, it contains the history field. So this is the fracture term. And this is the, again, this is another fracture term containing grad of phi. Okay. F external, F internal are these. K phi and Ku. K phi is essentially this K phi phi and Ku is Ku u. So they come out to be these expressions. They are long expressions. So They are of course derivable. If you convert this entire problem to the finite element formulation, you will be able to easily derive them. So another way of writing this stiffness matrix, which I showed you, this one, the overall stiffness matrix, can be this, where you multiply a constant omega with only the coupled terms. So if you remember, the overall aim of the staggered formulation is to decouple the coupled problem in phase field and displacement, correct? So we don't need these terms. And if we don't need these terms, we can always write the overall stiffness matrix in this form by just multiplying a constant omega. So when omega equals to 1, we have these set of equations, correct? Now this omega can be used as a tuning parameter, which goes from 0 to 1. So when omega is equals to 0, we essentially get a decoupled stiffness matrix, correct? So this can be written as this plus omega into this. So when omega equals to 0, we can get only the decoupled stiffness matrix. And this decoupled stiffness matrix is used in the staggered formulation. So essentially, this overall stiffness matrix gets reduced to a decoupled form like this, only because of omega. Okay. So how do we implement this in Abacus standard? So this is essentially not a dynamic formulation. So we have to use Abacus standard to solve these kind of phase field models. Again, when dynamic implementation will be discussed, then we'll be using Abacus explicit, but that's quite, in the distant future. So right now we are in the static or quasi-static regime. So we will be using Abacus standard. So we have three different problems: phase field problem, displacement problem, and history field problem. History field problem is essentially an erroneous word, but yeah, so we have the history field layer. So these three are individually called first, second, and third layer. Okay. If you remember this diagram, this one, so this is your displacement layer, this is your phase field layer, and this is your history field layer. Okay. The first layer or the phase field layer has to be depicted, or when you want to solve something in the software Abacus, if it does not fit the predefined list of finite elements given in the software, you will have to define your own user element. Okay. So this phase field layer or the phase field element is not a standard element in Abacus. So standard element in Abacus are like plane stress element, plane strain element, then dynamic explicit elements, thermodynamic elements, and so on and so forth. But this phase field element is not a standard element in Abacus. So you have to define or create your own custom element, and you do that using a subroutine called user element subroutine, or UEL. It is a very involved process. I have a UEL which I can discuss with you later, but it will be, if I start discussing it, it will be its own video. But right now, you just know that you write a UEL to define a custom finite element, Yeah. Next, you have the displacement problem. So the displacement problem is essentially how you solve for your strains, your stresses, and displacements. And that can be easily done using a UMAT, or user material subroutine. User material subroutine essentially tells you, or tells Abacus, the constitutive model, the overall constitutive model of the specimen or of the material, and it can be used side by side with this UEL. It has to be used, in fact, because phase field problem and displacement problem, there is a history field problem which exchanges info. information between the first and the second layer, right? So you have to use UEL and UMAT side by side or together. So this history field problem is the third layer again, which exchanges information between the first and the second. And this is essentially written as a simple linear elastic element using a UMAT with negligible stiffness. Why negligible stiffness? Because we have already fed stiffness into the UMAT. Okay. We have already fed stiffness into the UMAT. So we don't need another layer having the same stiffness. So if you club them together, essentially what will you have? You will have double stiffness. So we don't use stiffness in the third layer because it just exchanges information. So if I show a diagram, you will be able to understand it better. So look at this diagram. You have the first layer. This is a diagram taken from this paper. If you want, you can go and look into it. This is the first layer. Your first layer is the phase field layer. The second layer is the displacement layer. And the third layer with negligible stiffness is the UMAT layer. Okay. So this is how the 3-layer sandwich model works. So all of the nodes, they have 3 degrees of freedom. Why? Because if we discuss 2D, you have three degrees of freedom, ux, uy and phi. Remember, phi is a scalar. But if you have 3D, you will have 4 degrees of freedom, ux, uy, uz and phi. Okay. But here they discussed it for the 2D element. That's why it's 3 degrees of freedom. So every node gets stiffness from the third degree of freedom. How? From the first layer. You see the arrow direction. The third degree of freedom is your phase field. So this node gets its phase field stiffness from the first layer, which is your phase field problem. And it gets its first and second degree of freedom, which is your displacement, from the second layer. So stiffness from the first and second degree of freedom is got from the second layer, which is the displacement problem. And stiffness from the third degree of freedom, which is the phase field, is got from the first layer, which is the phase field problem. And this layer, this no stiffness or third history field layer, essentially exchanges information between these two. Okay. Again, let me explain how the staggered formulation works. So we have essentially decoupled the entire, phase field formulation using finite element and these set of equations, correct? Where k phi u and k u phi are now 0 because this tuning parameter omega is considered to be 0. So you have the displacement field, you have the phase field, and at time t equals to 0, everything starts from 0. So there is no crack. Basically, your body is at rest and there is no fracture. Now you start loading it. When you start loading it, so phase field equals to 0, it reaches some value of phase field, and using this phase field value, you calculate psi 0 n plus 1. You remember what is psi 0? Psi 0 is the strain energy of the uncracked specimen. So using phi n, you calculate psi 0 n plus 1 and consecutively un plus 1. On the other hand, using un or psi 0 n, you calculate phi n plus 1. So if you look at just one path, suppose you have phi equals to 0, the entire body does not have any crack. It starts from phi equals to 0. It at some time step, it reaches phi n. Using phi n, you calculate psi 0 n plus 1 and eventually un plus 1. Now using these two, you will be calculating what? You will be calculating phi n plus 2 here. Now what about phi n plus 1? Phi n plus 1 will be calculated using un and psi 0 n. So this crisscross process is called the staggered formulation. So you are essentially, what you are doing is, using phi n, you are calculating phi n plus 2. And using un, you are calculating un plus 2. Is basically that. nothing else. So you have decoupled the entire phase field formulation and you are solving it in a crisscross manner. Okay. So this is how, this is one of the methods, how you solve the, the phase field problem. Again, there are many methods that are available out. Suppose you don't put omega equals to 0. You have omega equals to 1. So essentially what do you have? You have this entire stiffness matrix, right? This can also be inverted in order to calculate phi and u. And that is a monolithic formulation. So you are solving the entire coupled problem as it is. You are not decoupling it. Of course, computations will be very expensive, but your answers will be a little bit accurate. Like your force displacement responses will be a little bit accurate. But yeah, if you can expand computational, power, if you have that much power, you can always go for monolithics or you can go for staggered. It's okay. Or, something in between. That's entirely up to you. Now, I'll show some examples of some basic linear elastic brittle fracture problems, and I'll show the crack paths that we got from the phase field model. So, the first one is mode 2 fracture. You remember in the previous video, I showed you the mode 1 fracture and the 3-point bending specimen. So this is mode 2 fracture where we have a SENT specimen and we are giving a shear displacement at the top surface. So what do you expect? You expect from your general fracture mechanics courses, you expect a crack that goes from here to here, right? At some angle. That angle is closer to 70 degrees. So using this phase field model, we got this crack where this angle was 64.5 degree. It generally, it generally varies from the 65 or 70 degrees. But if you have 64.5, you are good to go. That's okay. Next, we have a circular sample under mode 2K field. So how is it different from this? Essentially, now you have a circular sample with radius A and you load them with a displacement field over this entire circumference. Okay, this entire circumference. What will be the expressions? The expressions are from the Williams stress field formulation from fracture mechanics. So UI is K2. K2 is your mode 2 stress intensity factor, root 2 into square root of root 2 pi r by 4 mu pi into some angular displacement functions given by these expressions, where theta is the angle from the x-axis or from the r-axis. Okay. So again, we saw a crack at an angle. We observed that beta, now we got an angle of 77 degrees. We were assured of pure mode 2. Why? Because in these kinds of problems, there is always a doubt whether we can achieve pure mode 2 or not. Because if you have a slight bit of mode mixity, this beta angle will vary. So here it is very difficult to ensure pure mode 2. But if you give your boundary conditions in this way, using angular functions, you are almost certain that you are imparting pure mode 2. That's why we are assured of pure mode 2. Beta, we got 77 degree. And as the mode mixity K2 by K1 is changed, beta can vary. Next, we have an interaction of crack with hole. So essentially, you have a compact tension specimen with an initial notch and you have a hole offset from the center line. Okay. So what do you expect? You expect the crack to originate from this notch and be attracted to this hole, correct? How long? If the hole is at a much greater offset, then it will be not attracted. But if it is near to the crack, it will of course be attracted. Try it out with a piece of paper, cut out a hole and tear very close to the hole. You will see that the crack will be attracted towards the hole. But tear very far away from the hole, the crack will not be affected by the hole. So that is how we saw in the phase field model. Again, the crack is attracted by the hole. It goes, it enters the hole and it exits from a certain different part from the hole. And this is reminiscent of an experiment done by FAM, where this is a epoxy plate where they propagated the crack from the notch and they saw that this part is actually attracting the crack. Okay. Next, we have an asymmetric double edge notch tension specimen. So you have again a specimen with two notches at the edge. That's why it's called edge notch tension sample. Tension, why? Because we are pulling it through tension. But this is your center line and they are offset, like 1 mm offset from the center line. So what do you expect? How can the crack grow? Surprisingly, we saw this beautiful crack. So there are two cracks which originates from these two notches and they grow away from each other and finally they are attracted to each other. Like if you propagate these cracks even further, you will see that these cracks will meet. Okay, but there are also different patterns that you can observe in this problem. If your loading rate, your displacement is very high, you will see that these cracks, they initially meet. So from this stage they will form a S. They will eventually meet. They will not go over one another. But if your loading rate is lower or if your displacement is lower, only then you will be able to see this pattern. Try it out for yourselves. You will be surprised. So these kinds of cracks you can see in tree barks. And also Mellin performed an experiment using PMMA and they observed these cracks. You see, one crack on top of another, they are not meeting and they are originating from two offset notches. The last example is a notched bi-material. So you have a specimen again, but you have two materials. One, you have a weaker material where this E1 is lesser than E2. Here you have the tougher material. Here you have the weaker material. The GC is also weak. Here the GC is more. E2 is more. E1 is less. Okay. And you have a notch in the weaker material. And you pull it in tension. So what do you expect? Again, you expect the crack to grow. Then as it comes to the interface, this interface is not modeled explicitly. This is just a hairline interface. So essentially these two, these two materials are just placed side by side. Think of it like this. This interface is not modeled. This interface does not have any properties. Okay. So the crack will propagate straight through the weaker material, and when it hits the interface of the stronger material, we saw a crack split. So this crack, it branches into two, goes up along the interface till some distance, and it again enters the stronger material. And if you propagate this even further, these two branches will meet and they will travel along the center, as you expect in a mode 1 crack. But in the middle, near to the interface, you will see crack branching and crack meeting. So if you look at the force displacement curve of this problem, this is the force displacement response of the problem, you will see that it grows linear, then it grows non-linear with a decreased slope. Why? Because here the crack was being resisted, correct? The crack was being resisted, then it split. It split, that's why you get this drop. Then you get a sharp decline, then it's okay. So observations, the reaction force decreased as critical force is reached. Critical force means the peak. And as the interface is reached, energy required for splitting the crack is less than that required for traveling into the tougher material. Which is obvious because the crack will always take the path of least resistance or least energy. So the crack sees that traveling along the interface is energetically favorable. That is why it chooses that path. It branches itself and goes along the interface. And when it sees that it is favorable to enter the tougher material, it again branches and enters into the tougher material. That's it. It will always travel along the path of least resistance. Okay. So this is the final example that I was going to show you. In the next video, I will discuss how do you decide phase field parameters. Like GC is a material parameter which you cannot change, of course, right? But in all of these examples, I have not told what is LC, the length scale parameter. The length scale parameter is the width of your crack, right? The width of your phase field contour. So how do you select LC? I have a way to select LC, but then I'll discuss it in the next one. So bye bye and thank you for watching.